Welcome to the Deep Dive. Today we're venturing into the surprisingly intricate world of cannabis. We've pulled together a wide range of articles and research to really get under the skin of this plant.
Yeah.
Exploring everything from its, ancient beginnings right up to its current legal status and all the fascinating bits in between.
It's quite a story. Spans millennia, really, and it's still being written. So whether you're completely new to this or maybe you already know a fair bit.
Right.
Our goal here is basically to distill the most crucial information for you, but without, burying you in jargon.
Think of it as your express route, a shortcut to getting a solid handle on cannabis.
Exactly, a shortcut.
Okay, let's jump right in then. Cannabis, it's got a whole dictionary of nicknames, hasn't it? Marijuana, weed, pot, ganja.
Oh yeah, loads of them.
What's the fundamental thing we're actually talking about here?
Well, at its core, cannabis refers to a plant, the cannabis plant, to be precise, and the various non-chemically uniform psychoactive compounds it produces. It originated, we think, in Central or South Asia.
Right.
And what's remarkable is just how long it's been a companion to humanity. I mean, thousands of years.
Oh.
Its uses have gone way beyond just recreation. We're talking spiritual practices, traditional medicine. It's quite embedded.
Thousands of years. That really shifts your perspective, doesn't it?
It does.
And the word cannabis itself, that has a history too.
It does indeed, yeah. The word's roots, they seem to trace back to the Scythian language. The ancient Greeks even wrote about the Scythians using it in their funeral rituals.
Ah, interesting.
And what's really intriguing is the possibility of even older connections, maybe linking to Akkadian, like Hunbu, or even the Hebrew term kanabosum.
So this plant has been woven into the fabric of human history for a very, very long time.
Definitely.
Now, when we think about how it affects people, what are the key chemical players involved? What's actually doing the work?
Right. Well, the main character, the one that gets most of the attention for the psychoactive effects, is tetrahydrocannabinol, THC.
THC. Okay. The famous one.
That's the one. But it's really more like an orchestra. THC might be the lead instrument, but there are many others playing along.
Ah.
We've identified 483 known compounds in the plant so far.
483. Wow.
Yeah. And that includes at least 65 other cannabinoids. The most famous of those is probably cannabidiol, or CBD.
Right, CBD. We hear a lot about that one too.
You do.
So THC gets the spotlight for the high, but it sounds like there's a whole chemical ensemble working within that plant.
Precisely. It's complex.
And how do people actually consume cannabis? There's more than just, smoking a joint, sure.
Oh, absolutely. The ways people use it are pretty diverse.
Yeah.
And many of them involve heating it, which is important because that converts the THCA into the active THC.
Ah, okay. That heating step is key.
It is. So smoking is common, of course, pipes, bongs, joints, blunts, you name it. Vaporizing is another popular way. That heats it just enough to release the active compounds as a vapor without actually burning the plant material.
Less smoke. Potentially.
Potentially, yeah. Then you have edibles. That's where cannabis is incorporated into food. Bang in India is a really traditional example of that.
Right. Edibles.
Yeah.
They have a bit of a reputation for being strong or unpredictable sometimes.
They can be, yeah, because the absorption is different. Cannabis tea is also used, though THC doesn't dissolve well in water, so it's often made with fats like butter or milk.
Okay.
And then you get into extracts, things like tinctures, sometimes called green dragon, and concentrated hash oil. Those are other ways people consume it.
So quite a spectrum of methods. Now let's get into what happens once it's in the system. What are the typical mental effects people might experience?
Okay, the mental side. It can be quite varied, really. Feelings of euphoria are common, obviously, along with altered perceptions like how time feels and just general changes in your state of mind. A lot of users find it harder to concentrate, and short-term memory can definitely be impaired.
Right.
But, and this is important, at higher doses, or just in certain individuals, it can also trigger things like anxiety or even delusions.
Delusions? Like what?
Like someone might misinterpret events, thinking they're personally directed at them when they're not. Hallucinations can happen too, panic attacks, feelings of paranoia.
Wow.
And in some cases, even psychosis. It's a really complex area, though, and the exact link between cannabis use and psychosis is still being heavily researched and debated.
That's a really crucial point to underline. The link isn't fully understood yet.
Not fully, no.
And it's not just a mental thing, is it?
Yeah.
What about the physical effects?
Not at all, no. Physically, cannabis can affect your coordination and balance impaired body movement.
Okay.
Relaxation is a big one for many people. And of course, increased appetite, the famous munchies.
Can't forget the munchies.
Definitely not. It also usually leads to an increased heart rate. It can sometimes make breathing feel difficult, cause nausea for some. Dry mouth is very common. And those characteristic red eyes.
Right, the telltale sign for many. And how quickly do these effects typically start?
Yeah.
And, how long do they stick around?
Good question. When it's smoked or vaporized, the effects usually kick in pretty fast, like within minutes.
Okay.
But if it's eaten, say, in an edible, it takes much longer. Up to maybe 90 minutes sometimes.
90 minutes. Why so long?
Because it has to go through your digestive system first, get absorbed into the bloodstream that way.
Makes sense.
And as for how long they last, generally the effects can linger for anywhere from, say, 2 to 6 hours. Depends on the dose, the person's metabolism, how they consumed it. Lots of factors.
2 to 6 hours. That's a pretty significant window of effect.
It is.
Are there potential downsides, risks associated with using cannabis over the longer term?
Yes, definitely. There are potential long-term concerns. Developing an addiction, or what's clinically known as cannabis use disorder, is a real risk for some people.
Okay, addiction is possible.
It is. And there's evidence suggesting that starting regular use, especially during adolescence, might negatively impact mental abilities later on.
Right, the developing brain concern.
Exactly. Physically, chronic coughing is common for heavy smokers, a greater risk of respiratory infections too. And then there's a condition called cannabinoid hyperemesis syndrome.
What's that?
It's characterized by really severe, persistent nausea and vomiting. It can be quite debilitating for those who get it.
That sounds awful.
It really does. And it's also really important to mention a recent study from 2025, actually.
What did it find?
It found a nearly threefold increase in mortality over 5 years and a significantly higher risk of suicide among people diagnosed with cannabis use disorder.
Threefold increase in mortality. That's staggering.
It is. And separately, research coming out of Canada post-legalization has pointed to a rise in cases of schizophrenia and psychosis linked to problematic cannabis use.
Those findings certainly give you pause, don't they?
They do.
It highlights that while some might see it as, relatively harmless, there are potentially significant risks, especially with regular or problematic use patterns.
Absolutely. Context and pattern of use are key.
Okay, let's shift focus a bit. How widespread is cannabis use around the globe? Do we have numbers on that?
We do, although global figures can be hard to pin down perfectly. Based on data from around 2013, the estimate was people had used cannabis in the past year.
Wow, that's a huge range, but still. Yeah. A lot of people.
It is. It represents roughly 2.7% to maybe 4.9% of the global population aged 15 to 65.
And that makes it?
That makes it the most commonly used drug worldwide that is still largely illegal in many places.
Right. Most common, largely illegal drug.
Yeah.
Interesting. Which countries had the highest rates back then?
At that time, countries reporting the highest rates of adult use included Zambia, the U.S., Canada, and Nigeria.
Okay. And I've heard, anecdotally maybe, that the cannabis available today is often much stronger than it was, say, back in the 70s or 80s. Is that true?
That's absolutely accurate, yeah. Since the 1970s, there's been a very clear trend, especially in illicit markets, of increasing potency.
Meaning higher THC.
Exactly. Higher THC levels generally, and often lower levels of CBD concurrently.
And why is that?
A lot of it comes down to cultivation techniques, selective breeding, the rise of indoor growing operations specifically designed to maximize THC content.
So it's a more potent product people are often encountering now.
In many cases, yes. And that shift in the THC-CBD ratio can significantly impact the user's experience and potentially the risks.
Right. Okay, let's dip back into that historical context. You mentioned its use goes back centuries, millennia even. What do we know about its earliest applications? And when did the legal clamp start coming down?
Okay, history. The cannabis plant itself has been cultivated for a very, very long time, at least since the 3rd millennium BCE.
Wow. What for, initially?
Initially, mostly for practical things, making fabric, rope, hemp, basically.
Ah, right.
But evidence of its use for psychoactive effects, like burning it, dates back roughly 2,500 years, found in the Pamir Mountains in Central Asia.
2,500 years ago. Amazing.
It is. Now, legal restrictions. They are a much more recent phenomenon in the grand scheme of things. Started popping up in some regions around the 14th century.
14th century? Still quite a while ago.
Relatively, yeah. But it wasn't until the 20th century that widespread prohibition really became the global norm.
The 1900s, okay.
And then quite recently, we've seen a reversal of that trend in some places. Uruguay, interestingly, became the first country in the world to legalize recreational cannabis use back in 2013.
Uruguay, first mover.
Yep. And several others like Canada, Germany, Thailand have since followed suit in various ways.
And the U.S.
Yeah.
It's famously complicated there, right?
Extremely complicated. You've got many states allowing medical or even recreational use, but at the federal level, it's still classified as a Schedule I substance, a real patchwork.
Schedule I, meaning high potential for abuse, no accepted medical use. Federally, anyway.
That's the federal classification, yes, despite state laws.
It really is a mix of legal approaches across the globe and even within countries. Now, let's think about how cannabis is used today. We've touched on recreational, but what about medical applications, spiritual uses?
Right. Medically, cannabis, often called medical marijuana, is being explored for various conditions. Though, as we mentioned, research has been hampered by its legal status for a long time.
What sorts of conditions?
There's some evidence suggesting it can help with nausea and vomiting, especially during chemotherapy. Also, stimulating appetite, particularly in people with HIV/AIDS, and managing chronic pain and muscle spasms.
Okay, so some specific potential uses.
Yes, but the scientific backing is still developing for many applications. Medical use is legal in a limited number of countries and U.S. states, usually requiring a prescription and operating through regulated dispensaries.
So potential therapeutic benefits, but the science is still catching up, partly due to restrictions.
That's a fair summary.
What about spiritual uses? You mentioned ancient practices. Does that continue today?
It does, absolutely. Spiritually, cannabis has this deep history as an entheogen.
Entheogen.
A substance used in religious or spiritual rituals to facilitate spiritual experiences. In the Indian subcontinent, its sacred status goes way back to the Vedic period, maybe around 1400 BCE.
Wow.
The Hindu god Shiva is traditionally associated with cannabis. You often hear him called the Lord of Bang.
Right, bang, the edible preparation.
Exactly. And in more modern times, the Rastafari movement famously incorporates cannabis as a sacrament. They see it as aiding meditation and spiritual reflection.
It's really remarkable how deeply embedded it's been in various cultural and spiritual traditions over time.
It truly is.
Now, we've mentioned some negative effects already, but let's maybe dig into those a bit more systematically. Starting with the short-term adverse effects. What can go wrong right after using it?
Okay, short-term risks. Anxiety is a common one, even escalating to panic attacks for some people. Attention and memory can definitely be impaired, as we noted. And there's an increased risk for some individuals of experiencing temporary psychotic symptoms.
Like paranoia or hallucinations.
Exactly. Cannabis also clearly affects motor skills and reaction time. That's why driving while impaired is so dangerous. THC is found very frequently in drivers involved in accidents.
A major safety concern.
Absolutely. Other common immediate side effects? Dry mouth, red eyes, maybe dizziness, fatigue, sometimes even vomiting.
Okay.
And in rare cases, usually with very high doses, someone might experience what's called acute psychosis, which can actually last for several days.
Days. Wow.
Yeah. And with legalization and edibles becoming more common, there's also a growing concern about accidental ingestion by children.
Right, kids getting into gummies or brownies.
Precisely. And that can lead to serious health issues, often requiring emergency care because the doses can be very high for their small body weight.
Those immediate risks are definitely important for people to be aware of, especially parents. What about the potential for fatalities being linked to cannabis use? Is that something that happens?
It's a complex question. Direct cardiovascular deaths solely caused by cannabis use aren't clearly established in the way they are for, say, opioid overdoses.
Okay.
However, a 2019 review did suggest it could potentially be a contributing factor in some sudden deaths, mainly because it increases heart rate and can put strain on the cardiovascular system.
So maybe not the sole cause, but a potential factor in vulnerable individuals.
Potentially, yes. Also, deaths have been reported in connection with that cannabinoid hyperemesis syndrome we talked about, usually due to complications like dehydration or electrolyte imbalance from the severe vomiting. And as we touched on earlier, there's that observed link between cannabis use and suicide, particularly among younger users. And that recent 2025 study showing significantly higher mortality risk for those with cannabis use disorder, including a tenfold increase in suicide risk specifically.
That mortality and suicide data is, Well, it's deeply concerning.
It is. It underscores that problematic use patterns can have very severe consequences.
Okay, moving on to the longer-term adverse effects. There's always a lot of discussion about its impact on the brain, on mental well-being over time. What does the research show?
Right. Long-term psychological effects. A 2015 analysis looked at multiple studies and found that memory can be affected in regular users, both recalling past events, that's retrospective memory, and remembering to do things in the future, prospective memory.
So both types of memory.
Both seem to be impacted, yeah. Although some of these deficits might improve if someone stops using for a prolonged period.
Okay, some potential for recovery there.
Some, yes. Research also suggests potential lasting difficulties with what we call executive functions.
Executive functions? Like planning.
Exactly. Planning, problem-solving, decision-making. Especially in individuals who started using heavily when they were young or who are older long-term users.
And what about the IQ debate? Does long-term use lower intelligence?
That's a controversial one. There is correlational evidence suggesting a potential link between heavy, long-term use starting in adolescence and a decline in IQ scores later in life.
Correlational, meaning it's an association, not necessarily cause and effect proven.
Precisely. It's hard to definitively prove causation because so many other factors could be involved. Some studies have also linked heavy use with a reduced overall quality of life, but again, the direct cause and effect isn't always crystal clear.
Okay. And what about looking directly at the brain? Have brain imaging studies given us any insights?
They have. Neuroimaging studies have pretty consistently shown a reduction in the volume of the hippocampus in chronic cannabis users.
A hippocampus. That's crucial for memory, right?
Exactly. It's a key memory center. Findings regarding the amygdala, which is involved in emotions, are a bit less consistent across studies.
Okay.
Interestingly, some studies have actually observed increased activity in certain brain regions when users perform cognitive tasks.
Increased activity. Is that good?
It might actually be the brain working harder, trying to compensate for less efficient processing caused by the cannabis use.
Ah, like a compensatory effort.
Possibly, yeah. There's also clear evidence for what's called downregulation of CB1 receptors in the brain.
Downregulation. Meaning fewer receptors.
Fewer or less sensitive receptors. Those are the main receptors THC binds to. The good news here is that this seems to return to normal after about a month of abstinence.
So the brain can readjust receptor levels if use stops?
It appears so, yes.
It sounds like the brain definitely adapts to long-term cannabis exposure, but maybe not always in beneficial ways.
That seems to be the case.
What about the potential for becoming dependent or addicted? How common is that?
Dependence, or cannabis use disorder, is definitely a recognized condition. According to the older DSM-IV criteria, estimates were that around 9% of people who try marijuana eventually develop dependence.
9% overall.
Yes. But a 2013 review estimated that figure jumps much higher, maybe 10 to 20%, among those who use daily.
Okay, so daily use significantly increases the risk.
Absolutely. And withdrawal symptoms can occur when heavy users stop.
Withdrawal, like with alcohol or opioids.
Generally milder than those, but still unpleasant. Things like trouble sleeping, irritability, feeling anxious or depressed, cravings for cannabis.
Okay. Are there factors that make someone more likely to become dependent?
Yes. Research suggests some risk factors. Things like a history of poor academic achievement, behavioral problems in childhood or adolescence, difficult relationships with parents, or having a family history of substance abuse issues.
So while not everyone who uses becomes addicted, it's a real possibility for a significant minority, especially frequent users.
That's right.
Now, what about links between cannabis use and other mental health conditions, like psychosis or depression?
Okay, the psychiatric links. There are sort of two main areas of concern researchers focus on. First, those temporary psychotic reactions that can happen during or right after use, sometimes called cannabis-associated psychotic symptoms, or CAPS.
Right, the short-term ones we meant.
Exactly. Second, there's the potential link to an increased risk, or perhaps an earlier onset, of more persistent psychotic disorders, like schizophrenia.
Okay, the long-term psychosis risk. What's the evidence there?
Epidemiological studies looking at large populations have generally shown a relationship. More cannabis use, especially high-potency cannabis started young, seems linked to a higher risk of developing psychosis.
Seems linked. Again, causation is tricky.
Very tricky. It's a complex interplay. Is cannabis triggering psychosis in vulnerable people? Are people prone to psychosis more likely to use cannabis? Or is there some shared underlying factor? The debate continues.
Right. What about depression and anxiety?
Cannabis use might also increase the risk for developing depression or anxiety disorders in some individuals. But again, proving a direct causal link from cannabis to depression or anxiety hasn't really been established definitively. It could go the other way, people using cannabis to self-medicate existing conditions.
Okay.
And importantly, a major 2019 review concluded there's just not enough good evidence right now to say that cannabis is a safe or effective treatment for pre-existing mental health disorders like depression, anxiety, or PTSD.
Despite some claims you might hear.
Despite those claims, yeah, the high-quality scientific evidence isn't there yet.
It seems like the whole interplay between cannabis and mental health is incredibly intricate and definitely needs more research.
Absolutely. High-quality research is crucial.
Okay, turning our attention now to physical health. What are the potential long-term concerns there for regular heavy users?
Physically, long-term heavy use has been associated with potential problems affecting the liver, the lungs, the heart, and blood vessels.
A range of organs.
Yes. Interestingly, some users report substituting cannabis for other substances they see as more harmful, like opioids, alcohol, or tobacco, sometimes leading to reduced use of those other drugs.
An interesting substitution effect for some.
For some, potentially, but back to the downsides, that cannabinoid hyperemesis syndrome, the severe vomiting. That's a significant physical consequence for those affected. And tragically, as mentioned, fatalities have been reported in connection with it.
Right. What about the lungs, specifically from smoking?
Chronic heavy smoking of cannabis is definitely linked with increased respiratory infections and symptoms of bronchitis, cough, phlegm production.
Similar to tobacco smoking effects.
Some similarities, yes. Cannabis smoke actually contains many of the same carcinogens, cancer-causing chemicals found in tobacco smoke.
So does it increase lung cancer risk?
That's where it gets murky. Despite the presence of carcinogens, there isn't currently a clear scientific consensus that smoking cannabis significantly increases the risk of lung cancer in the same way tobacco does. Research is ongoing, and results have been mixed.
Interesting. Any other physical health links?
There's some suggestion of a potential link to a specific type of testicular cancer germ cell tumors. Also, a possibility that cannabis could interfere with how well anticoagulant medications, blood thinners, work.
Okay, so quite a few potential physical health considerations too. What about emergency room visits related to cannabis? Have those changed, maybe with legalization spreading?
They have. Data showed a pretty significant rise in emergency department visits linked to cannabis use in the U.S. between roughly 2012 and 2016.
A significant rise. Who's most at risk?
Adolescents seem to be at the highest risk for needing emergency care related to cannabis.
And why are people ending up in the ER?
Common reasons include acute psychiatric effects like extreme anxiety, paranoia, suicidal thoughts, and also those gastrointestinal issues, especially cannabinoid hyperemesis syndrome. Back in 2011 in the U.S., there were already a substantial number of ER visits where cannabis was implicated, often in combination with other drugs.
Those statistics really underscore the potential for acute negative outcomes needing immediate medical help.
They do.
Are there any specific concerns around reproductive health? Or maybe the effects of secondhand cannabis smoke?
Yes, on both counts. Cannabis use during pregnancy is definitely seen as a growing public health concern. Research suggests possible links to negative outcomes for the child, things like effects on cognitive development, mental, and physical health. Using while breastfeeding might also pose risks.
Okay, so risks during pregnancy and breastfeeding. What about secondhand smoke? Is that a worry like with tobacco?
It seems it could be. A 2022 study produced some pretty startling findings. It looked at bong smoking in an enclosed space and found it dramatically increased the levels of fine particulate matter, PM2.5, a known carcinogen, to levels many times higher than what's considered hazardous air quality.
Higher than hazardous levels.
Yes, and significantly exceeding the levels typically found from secondhand tobacco smoke in similar conditions.
Wow. That suggests a real potential health risk for non-smokers who might be exposed, doesn't it?
It certainly does, especially in poorly ventilated indoor environments. It's a relatively new area of research, but definitely concerning.
That's a really important finding, especially as use might become more common or normalized. Okay, let's maybe shift gears slightly and get into the pharmacology. How does THC actually work in our bodies at a biological level?
Right, the mechanism. THC primarily interacts with what are called cannabinoid receptors in our bodies, specifically CB1 receptors.
CB1 receptors, where are they?
They're mainly found in the brain and central nervous system, but also in some other tissues. Think of them like docking stations on cells.
Okay.
Now, THC doesn't bind perfectly to these CB1 receptors. It's what scientists call a weak partial agonist.
Weak partial agonist, meaning?
Meaning it activates the receptor, but not to its maximum possible extent, and maybe not as strongly as the body's own natural cannabinoids, called endocannabinoids. But even this partial activation triggers changes in how brain cells communicate, leading to the psychoactive effects.
Okay. And what about CBD? How does that work?
CBD is different. It doesn't bind strongly to CB1 in the same way. In fact, it can act as a CB1 receptor antagonist or negative allosteric modulator.
Antagonist. So it blocks it.
It can block or reduce the effects of THC at that receptor. It also interacts with other receptors in the body, like serotonin receptors, and its mechanisms are still being actively researched. It's quite complex.
So THC activates CB1, leading to the high, while CBD might block or modulate that, and does other things too.
That's a simplified way to put it, yes. THC's action on CB1 disrupts normal brain signaling, affecting mood, perception, memory, and so on. It also indirectly causes an increase in dopamine release in certain brain areas.
Ah, dopamine, the reward chemical.
Exactly. That contributes to the pleasurable and potentially reinforcing effects. CBD also interacts with opioid receptors, but the full significance of that isn't totally clear yet.
It sounds like there's still a lot to learn about exactly how all these cannabinoids work together and individually.
There really is.
What about how these compounds travel through our system and how long they stick around?
Well, cannabinoids, both THC and CBD, are highly lipophilic,
Lipophilic.
meaning fat-loving. They dissolve well in fats. This means they can get stored in the body's fatty tissues.
Ah, okay.
And because of this, they can remain detectable in the body for quite a long time, much longer than many other drugs. Even after a single use, THC metabolites can be found in urine for days or weeks, and in heavy users for much longer.
Weeks. Wow.
Yeah, it depends on the amount used, frequency, body fat percentage, and the sensitivity of the test. It's thought that this accumulation in fatty tissues, including the fatty membranes of nerve cells, might contribute to some of the longer-term effects.
That explains why drug tests can pick up cannabis use long after the immediate effects have worn off.
Exactly. It lingers in the fat stores.
Okay, let's touch on the chemistry of cannabis itself.
Right here.
How is the active THC actually formed? You mentioned heating was important.
Right. In the raw cannabis plant, you don't actually find much psychoactive THC. What you find is its precursor, tetrahydrocannabinolic acid, or THCA.
THCA, so not psychoactive itself.
Generally considered non-psychoactive, yes. When you apply heat through smoking, vaping, or cooking in edibles, THCA undergoes a chemical reaction called decarboxylation.
Decarboxylation.
Sounds technical.
It just means it loses a carboxyl group, a little cluster of atoms. That conversion process turns the non-psychoactive THCA into the psychoactive THC.
So heat activates it. That's the key step.
That's the key chemical transformation for the main psychoactive effect. And remember, THC is just one of those hundreds of compounds in the plant.
Right, the 483 you mentioned.
Including at least 65 cannabinoids, it's a complex chemical factory.
How do we actually detect THC or its use in people's bodies?
Specialized lab techniques are needed. They test bodily fluids, blood, urine, hair, saliva, even sweat. They're usually looking for THC itself or its main inactive metabolite, THC-COH.
THC-COH.
Yeah, that's what the body breaks THC down into. And it stays around for quite a while, especially detectable in urine.
Can these tests tell you how much someone used or when? They can give some indication. For example, detecting THC itself usually indicates more recent use than detecting only THC-COOH. The levels might suggest heavy versus infrequent use, but they generally can't perfectly pinpoint the time of use or the exact dose, and importantly, they can't distinguish between legally prescribed medical use and recreational use.
So limitations exist. What tests detect what?
Generally, urine tests primarily detect the THC-COH metabolite. Hair tests can show a longer history of use, maybe months. Saliva and sweat tests tend to reflect more recent THC exposure. Blood can contain both THC and its metabolites.
Okay. Are there simpler tests used, maybe by law enforcement?
There are field tests, like the Duquesnoy-Levine test, which gives a color reaction. But these are just presumptive tests, not conclusive on their own. They need lab confirmation.
Right. And I've heard rumors about ways to beat drug tests, like taking zinc supplements. Is there anything to that?
There's some debated research suggesting zinc supplements might interfere with the detection of THC metabolites in urine tests by masking them somehow. But it's not a guaranteed method, and labs are often aware of potential adulterants.
So not a reliable workaround.
Definitely not something to rely on.
Okay. Now, the world of cannabis strains and varieties seems incredibly complex and, frankly, confusing sometimes.
Right.
You hear about sativa and indica all the time. What's the deal with those?
Yes, sativa versus indica. The traditional lore is that sativa strains are more energizing, give you a head high, maybe more creative, while indica strains are supposed to be more relaxing, sedating, a body high.
That's the common wisdom, yeah.
It is. However, scientifically, this distinction is now considered pretty unreliable by many researchers.
Why?
Because when you actually analyze the chemical profiles, there isn't a consistent pattern linking those labels, sativa indicas, to specific chemical makeups or predictable effects. The growing conditions, the harvesting time, the specific cannabinoid and terpene profile, those seem much more important than just the supposed lineage.
Terpenes. What are those?
They're aromatic compounds found in cannabis and many other plants. They contribute to the smell and taste, but researchers now think they might also interact with cannabinoids to influence the overall effects, something called the entourage effect.
Interesting. So the sativa indica thing might be more marketing than science.
Largely, yes. A 2015 review actually suggested that the ratio of CBD to THC in a particular sample might be a much better predictor of its effects.
Ah, the CBD-THC ratio again. What did it find?
It found that strains with a higher CBD to THC ratio were generally associated with fewer reports of positive psychotic symptoms, maybe better cognitive function during use, and potentially a lower risk or later onset of psychosis compared to low CBD, high THC strains.
So the actual chemical balance seems key, maybe more than those old labels.
That's what the evidence increasingly suggests, yes.
What about the actual strength, the THC percentage, in different types of cannabis products? Is there a standard range?
It varies hugely. According to the UN Office on Drugs and Crime, typical cannabis flower, the buds people smoke, might contain around 5% THC on average globally, historically speaking.
Only 5%. That sounds quite low compared to what you hear about today.
It is, compared to modern potent strains. Resin, like hashish, might average closer to 20% THC. And cannabis oil, those concentrated extracts, can easily exceed 60% THC, sometimes much higher.
60% or more. That's a massive difference from 5%.
It's a huge difference. And as we discussed, the potency of illicit cannabis in particular has generally climbed significantly since the 70s. Higher THC, often lower CBD.
Driven by those indoor growing techniques.
Largely, yes. Techniques optimized purely for maximizing THC. Within the plant itself, the flower buds have the highest concentration, then the leaves. The stalks and seeds have very low levels.
Okay, and this rise in potency has had real-world consequences, right, like in the UK?
Yes, the UK government actually reclassified cannabis to a stricter category, Class B, partly because of the prevalence of these high-potency strains, often called skunk there. They were concerned about the associated mental health risks.
Right, and you mentioned contamination earlier. Are there other things people should be aware of, like synthetic cannabinoids?
Absolutely, that's a major concern. Cannabis might be contaminated with pesticides, mold, heavy metals, depending on how it's grown. Or sometimes illicit dealers might lace low-quality cannabis with synthetic cannabinoids to make it seem stronger.
Synthetic cannabinoids, like spice or K2.
Exactly. Those are dangerous substances with unpredictable and often severe side effects, completely different from natural cannabis. Finding them laced into what someone thinks is just weed is a serious risk.
Definitely something to be extremely cautious about. It's a rapidly changing market, it seems, with potency and synthetics adding real layers of complexity and risk.
It really is. The landscape is constantly shifting.
Let's shift now to the different forms or preparations of cannabis that people might encounter. We've mentioned a few, but could you maybe list the main ones?
Sure. The most basic form is just marijuana, usually meaning the dried flowers, maybe some small leaves, from the female cannabis plant. That's what's typically smoked.
Okay, the dried flower.
Then there's kief. That's the powdery substance that collects in grinders, for example. It's rich in trichomes, those tiny sticky glands on the plant that actually produce the cannabinoids and terpenes. So kief is more potent than the flower itself.
Right, the trichome powder.
Exactly. If you press that kief together, you get hashish, or hash. Usually comes as a solid cake or ball. Again, more concentrated than flower.
Hashish, okay.
Tinctures are liquid extracts, often made by dissolving cannabis in alcohol, sometimes called green dragon. They're typically taken orally, like a few drops under the tongue.
Tinctures. And hash oil.
Hash oil is an even more potent, very viscous extract. Usually made using solvents like butane or CO2 to pull out the cannabinoids, can be extremely high in THC, often used for dabbing or in vape pens.
Right, the really concentrated stuff.
Then you have infusions. That's where you extract the cannabinoids into a fat, like butter or cooking oil. Cannabutter is a classic example. That infused fat is then used to make edibles.
Okay, for making brownies and such.
Precisely. And one more worth mentioning, particularly in parts of South America like Paraguay, is something called marijuana prensada, or paraguayo.
What's that?
It's basically low-quality cannabis compressed into bricks, often mixed with binding agents, sometimes even questionable adulterants. It's usually cheaper, but considered much lower quality and potentially more harmful due to contaminants.
Wow. So a really diverse range of preparations out there, from simple flour to highly potent extracts and, unfortunately, sometimes contaminated products.
A very wide spectrum, yes, each with different characteristics, potency levels, and potential risks.
Okay. Let's delve even deeper into the history now. We know it's ancient, but can we trace its journey a bit more, both the ancient world and more recent times?
Absolutely. As we said, its use for textiles, hemp fiber goes way back, Neolithic China and Japan.
Right. Practical uses first.
But the psychoactive side is ancient too. That evidence of braining cannabis in Romania around 3500 BCE, its ritual use might have spread with early Proto-Indo-European cultures moving across Eurasia.
Interesting. What about that Soma connection you mentioned?
Ah, yes, soma. This was a ritual drink mentioned in the ancient Vedic texts of India and Iran. Its exact identity is debated, but cannabis is one of the candidates proposed as an ingredient, though it's far from certain.
A historical mystery?
A bit, yeah. We know for sure, though, that ancient Assyrians used it, potentially for incense or medicine. The Scythians, as mentioned, used it ceremonially. Herodotus described them inhaling the vapor from heated hemp seeds in tents.
Right, the Greek historian.
Exactly. Ancient China used it medicinally for centuries. India has a long history with bhang integrated into religious festivals and everyday life. We find evidence in ancient Egypt, too. That 2,500-year-old evidence of actual smoking from tombs in the Pamir Mountains is quite definitive for psychoactive use.
So really widespread across the ancient world.
Very widespread. It was used by Sufi mystics in the Islamic world for spiritual practices. Ancient pipes found in Ethiopia dating back to the 14th century contained cannabis residue.
So a truly global ancient history. What about its journey into more modern times? How did it get to the West and then moves towards prohibition?
It was introduced to the New World, the Americas, by the Spanish in the 16th century, mainly for hemp production initially.
Okay.
Its psychoactive properties gained more attention in the West in the 19th century. You had figures like Dr. Jacques-Joseph Moreau in France, who studied its psychological effects and even formed the Club des Hachiciens in Paris, where literary figures experimented with it.
The Hash Eaters Club.
Exactly. And Dr. William Burke O'Shaughnessy, an Irish physician working in India, introduced cannabis extracts to British medicine for treating various ailments.
So medical interest grew in the 1800s. When did the legal shift happen?
Criminalization started creeping in earlier in some places, like Napoleonic Egypt banned it. But the big wave began in the late 19th and early 20th centuries, often tied to colonial powers or social anxieties. Mauritius banned it in 1870, Singapore later. The U.S. started restricting it state by state in the early 1900s, often linked to anti-immigrant sentiment. Canada banned it in 1923.
So the early 20th century was key for prohibition starting.
Yes, and international controls started building too. The 1925 Hague Convention included restrictions on cannabis trade. In the U.S., the infamous 1937 Marijuana Tax Act effectively criminalized it at the federal level, fueled by propaganda campaigns like Reefer Madness.
Right, the propaganda films.
Exactly. That really cemented prohibition for decades. The Netherlands took a notably different path in the 1970s, differentiating between hard and soft drugs and tolerating cannabis sales in licensed coffee shops, though cultivation remained illegal, a weird paradox.
The famous Dutch model.
Yes. And then, as we said, the big shift started more recently with Uruguay fully legalizing recreational use in 2013, setting a precedent. Canada followed in 2018, and now many U.S. states and countries like Germany and Thailand are moving in similar directions, albeit with different models.
It really is a history of extremes, from ancient acceptance to near global prohibition, and now this unfolding era of legalization and regulation in some parts of the world.
A very dynamic history, and it's clearly not over yet. The UN's World Drug Report continues to track all this production, trafficking, consumption patterns globally.
Okay, let's try to unpack some of the cultural, legal, and economic dimensions of cannabis today.
Yeah.
Culturally, how does it fit in?
Culturally, it's obviously been hugely popular as a psychoactive substance around the world, probably second only to alcohol and tobacco in terms of sheer numbers of users globally.
Right.
The anthropologist Vera Rubin described two main cultural streams. One is the sort of traditional folk use, often integrated into community life, maybe for medicine, ritual, relaxation, involving small-scale cultivation.
Okay, the traditional stream.
The other is a more contemporary pattern, often linked to larger-scale commercial production, maybe focus more on the psychedelic or intense psychoactive experience, sometimes tied to youth subcultures or specific music scenes. These two streams can overlap, of course.
Interesting distinction. Legally, we've touched on this, but what's the overall trend now?
The dominant trend for much of the 20th century was definitely towards stricter laws prohibiting cultivation, possession, sale. But in the last, say, 20, 30 years, the trend has become much more mixed.
How so?
You see many places reducing penalties, decriminalizing simple possession, so it's more like a traffic ticket than a criminal offense. And then, of course, the growing wave of outright legalization for medical use or for regulated recreational use like alcohol or tobacco.
So a move away from strict prohibition in many areas.
In many Western countries and some others, yes, but it's not universal. Some places are sticking with strict prohibition, and even historically tolerant places like the Netherlands have actually introduced some new restrictions recently, like limiting sales to tourists in some areas.
Right. So it's complex. What about the U.S. situation now?
Still very complex. More and more states have legalized recreational or medical use, but federal prohibition remains. There was recent news about the Department of Justice moving to reclassify cannabis from Schedule 1 to Schedule 3.
Schedule 3, what would that mean?
Schedule 3 implies it has accepted medical use and lower potential for abuse than Schedule 1 or 2 drugs. It would be a major symbolic shift and could ease restrictions on research and banking for cannabis businesses. But it wouldn't automatically make it legal nationwide for recreational use. State laws would still largely govern that.
So a potentially big step, but not full federal legalization yet.
Exactly. It's still unfolding. Globally, you have the fully legalized models like Uruguay and Canada, various decriminalization approaches, medical-only systems, and then places with incredibly strict laws and harsh penalties like Singapore or South Korea, where even using cannabis legally abroad can potentially lead to prosecution back home.
Wow. A real global patchwork. Economically, what's the scale of this?
The cannabis market, both legal and illegal, is massive, worth billions and billions of dollars globally. The development of sinsemilla, seedless, high-potency female flowers, and modern indoor cultivation techniques really transformed production and potency.
Right, leading to skunk and higher THC.
Exactly. Though there's some debate about how much average THC levels have truly risen versus just the availability of high-potency options increasing. Major producing countries are scattered across the globe: Morocco, Afghanistan, Mexico, increasingly North America in the legal markets. Prices vary hugely by location, quality, and legal status. We have seen prices tend to decline in markets after legalization, like in Colorado, due to increased supply and competition.
It sounds like the economics are a huge driver in the legalization debates, both for tax revenue and business interests.
Undeniably a major factor, yes.
Okay, let's tackle a somewhat contentious topic. The idea of cannabis as a gateway drug. What's the thinking behind that, and what does the evidence actually say?
Right, the gateway hypothesis. The basic idea is that using cannabis, often seen as a softer drug, somehow primes the brain or leads socially towards using harder, more dangerous drugs like cocaine or heroin.
And this was used to argue for prohibition.
Oh, definitely. It was a major pillar of prohibitionist arguments in the U.S. for decades. If you smoke pot, you'll end up shooting heroin, that kind of narrative.
So is it true?
Well, it's complicated. Statistically, it is true that many people who use drugs like heroin or cocaine also used cannabis first.
Okay.
But UT, and this is a huge but, correlation does not equal causation. Most people who use cannabis do not go on to use harder drugs, and people who use hard drugs often use alcohol and tobacco even before cannabis.
So maybe alcohol and tobacco are gateways too.
That's one counter-argument. Another important factor is the social context of illegality. Buying any illegal substance puts you in contact with illicit markets where other drugs might be available, so the illegality itself could be part of the gateway rather than the drug's pharmacology.
Right, the shared social environment of illegal drug use. Right.
Exactly. There's also the common liability to addiction theory. This suggests that some individuals just have an underlying predisposition, maybe genetic, maybe environmental, that makes them more likely to experiment with various substances. Cannabis might just be one of the first illegal ones they encounter because it's more widely available.
So it's not necessarily cannabis causing the progression, but an underlying vulnerability.
That's the idea behind the CLA model. A 2020 study from NIDIA, the U.S. National Institute on Drug Abuse, did find some evidence supporting the idea that marijuana could act as a getaway for some users by priming the brain's reward system.
Okay, so some biological priming effect possible.
Possible, yes, but that same study also highlighted that alcohol and nicotine can have very similar priming effects. So it's not unique to cannabis. The overall picture is that while cannabis use is statistically associated with later use of other drugs for some individuals, a direct causal link solely due to cannabis itself is not definitively proven, and many other factors are clearly involved.
It sounds like the simple gateway drug label is far too simplistic for a complex reality.
Far too simplistic, yes.
Finally, before we wrap up, what are some of the main challenges that scientists face when they actually try to study cannabis and its effects properly?
Conducting good, rigorous science on cannabis is actually quite difficult, surprisingly so.
Why is that?
The biggest hurdle, historically and still in many places, is its illegal status. This makes it incredibly hard for researchers to legally obtain cannabis for studies, especially cannabis that's standardized and representative of what people are actually using. Often, research cannabis has been low-potency stuff quite different from market cannabis.
Right. Hard to study what you can't legally access or possess.
Exactly. Then there are confounding factors. Many cannabis users also smoke tobacco, for instance. So if you're studying lung effects, how do you separate the impact of cannabis smoke from tobacco smoke? It's tricky.
Makes sense.
Recruiting participants can also be hard due to the stigma or legal fears. And even when people participate, getting truly accurate self-reports of how much cannabis they use, how often, what potency, that can be unreliable. People might underreport or simply not know the exact details of illicit products.
So legal barriers, confounding variables like tobacco use, and difficulties in getting accurate usage data all complicate the research.
Precisely. It means that interpreting the existing research often requires caution, being aware of these limitations. We need more high-quality, well-controlled studies, which are becoming easier in places with legalization, but still face challenges.
It sounds like the legal framework itself has created significant roadblocks to fully understanding the substance.
It absolutely has, for decades.
Well, this has truly been a real deep dive, hasn't it, into this incredibly multifaceted world of cannabis.
It really has covered a lot of ground.
We've gone from ancient history and diverse uses right through to the complex chemistry, the effects both desired and adverse, and this constantly shifting legal and cultural landscape.
Yeah, it's clear there are no simple answers when it comes to cannabis.
It really seems that way. It's a topic with so much depth, so much nuance, and it goes way beyond the simple narratives you often hear.
Absolutely. And understanding these complexities, these nuances, is just so vital as societies continue to grapple with how to approach cannabis, whether it's policy reform, medical use, or public health messaging.
So for you, our listener, what's the main thing to take away? Hopefully this exploration has given you a more thorough, maybe a more balanced perspective, helped you move beyond some of the, overly simplistic or maybe sensationalized information that's often out there. Perhaps it gets you thinking a bit more deeply about the implications of this trend towards higher potency, or the real complexities involved in legalization versus decriminalization, or even just the critical need for more good, unbiased scientific research in this area.
All really important points to consider.
This is definitely a conversation, a story that is still very much unfolding around us.
It certainly is.
Thanks for joining us on the Deep Dive.
Think for a moment about a creature you find, really captivating. Maybe it's a butterfly or a big cat or even some tiny insect. Now imagine that creature and so many others are really struggling just to survive.
It's a tough reality.
Yeah. So today we're doing a deep dive into endangered species. We want to understand what that term really means, what's causing it, and importantly, what's being done about it.
Right, we're pulling from a pretty detailed overview here. The aim is to really get the key facts, the main causes, look at what's happening in places like Brazil, the U.S., Canada, India.
Okay.
And hopefully you'll come away with a much clearer picture of, well, what's at stake and some of the surprising ways people are trying to help.
Okay, great. So let's start right there. Endangered species. We hear it all the time, but what does it actually mean scientifically? What's the definition?
Well, basically, it means a species is facing a really, really high risk of becoming extinct, disappearing forever, and that could be worldwide or sometimes just in a specific country or region. It ties into this idea of conservation status.
Conservation status.
Yeah, it's like a category that tells you how likely a species is to go extinct. A risk assessment, essentially.
So it's like a global danger list for animals and plants.
That's a pretty good way to think about it, yeah. And the big one everyone uses globally is the IUCN Red List.
IUCN.
International Union for Conservation of Nature. They maintain this huge database, the Red List, and it's kind of the gold standard for tracking how species are doing worldwide.
Okay. IUCN Red List. And I'm guessing it's not just endangered or not endangered. There are levels.
Exactly. It's a whole spectrum. So endangered, or EN, that's sitting between vulnerable, VU, which is high risk, and critically endangered, CR.
Critically endangered sounds bad.
It is. It means they're facing an extremely high risk, like right now in the immediate future. Think Amur leopards, they're CR.
Wow.
Then you have species that are doing better, relatively speaking. Near threatened, NT, or least concern, LC, their populations are healthier. Snow leopards, for instance, they're currently listed as vulnerable.
That really helps clarify the different stages. So globally, then, what's the big picture? I feel like I've heard some pretty alarming stats.
Yeah. The estimates are stark. Some suggest over half of all the world's species might be at risk of extinction.
Over half.
It's a huge number. But, we have to be a bit careful. It's incredibly hard to actually assess every single species. Think about the deep oceans, for example.
Right, so much we don't even know is down there.
Exactly. And the worry is species could be vanishing there before we even, properly identify them or understand their situation. A truly sobering thought.
Definitely. Are there international agreements trying to tackle this?
Yes, there are. About 195 countries have signed up to create biodiversity action plans. These are basically national strategies, roadmaps outlining how each country plans to protect its own threatened species. In the U.S., for example, they often call these species recovery plans.
Got it. So we know what endangered means. We have sense of the scale. Now, the big question, why is this happening? What's pushing all these species towards, the edge?
Well, the overwhelming answer, unfortunately, is us. Human activity.
Right. How specific?
Several big things, and they often overlap. Number one is probably habitat loss. Just destroying the places where animals live.
Like cutting down forests for farms or cities.
Precisely. Or draining wetlands, damming rivers. We convert natural landscapes, and the species that depend on them literally lose their homes, their food sources, their breeding grounds. Imagine your neighborhood just disappearing.
Yeah, nowhere to go. And I guess linked to that is poaching. Illegal hunting?
Absolutely. Poaching is still a massive problem. Killing animals illegally for, parts like ivory or rhino horn, or for the exotic pet trade, or even traditional medicine, it devastates populations, especially the rarer ones.
Okay, habitat loss, poaching, what else?
Then there are invasive species.
Ah, right. Species that don't belong in a particular ecosystem.
Exactly. Humans move plants and animals around the globe, sometimes intentionally, sometimes by accident. And when these non-native species get established somewhere new, they can wreak havoc.
How so?
Well, they might outcompete the native species for food or space. They might prey on native species that have no natural defenses against them. Or they can introduce new diseases. They just throw the whole natural balance off kilter.
Right, upsetting the whole system. And then, of course, there's the elephant in the room, climate change. How does that fit into species endangerment?
Oh, climate change is a huge, huge factor. And it's complex. The planet's warming up incredibly fast, faster than anything we've seen in, the last 10,000 years.
That fast.
Yeah. And species have to try and adapt to totally new weather patterns, different rainfall, more extreme events, temperature shifts. It's a massive stress.
And the CO2 itself, does that play a role beyond just warming?
It does. Rising carbon dioxide levels in the atmosphere are definitely linked to animal endangerment. Think about it. Before the Industrial Revolution, CO2 was typically below 280 parts per million.
Okay.
Back in 2014, it was already bouncing between 395 and 402 ppm. That's a major change, and it has knock-on effects. It's like giving the planet a fever.
Yeah.
Even a small temperature rise overall can cause big problems.
That's a powerful way to put it. So what are the direct effects on animals? How does this warding and extra CO2 impact them?
We're seeing all sorts of things. changes in where species can actually live, changes in their genetics maybe as populations try to adapt, shifts in behavior like when they migrate or breed, and ultimately it affects their chances of survival.
So they might have to move.
Yeah, many find their traditional homes just aren't suitable anymore. Too hot, too dry, food sources disappear. So they might try to migrate, but but they might not be able to. Maybe there's a city or a huge farm in the way that's habitat fragmentation. Or maybe the place they need to get to is already full of those invasive species we mentioned. It's tough.
Wow. I read somewhere like a huge fraction of species are at risk just from climate change.
There was a WWF study, suggesting something like 1 in 6 species could be threatened with extinction because of climate change if we don't make some serious changes.
1 in 6, that's staggering.
Yeah.
And it's not just on land, right? The oceans are feeling this too.
Oh, absolutely. All that extra CO2 we pump into the air, a lot of it gets absorbed by the oceans, and that makes the water more acidic. Ocean acidification.
And that's bad for marine life.
Very bad, especially for anything that builds a shell or a skeleton out of calcium carbonate. Think corals, shellfish, tiny plankton. The more acidic water makes it harder for them to build and maintain those structures.
Yeah.
It literally starts dissolving them in some cases. It's creating a hostile environment for so much marine life.
So can you give us some specific examples, like animals being hit hard by climate change right now?
Sure. Think about emperor penguins down in Antarctica. They absolutely depend on stable sea ice. It's where they breed, raise their chicks, molt, and rest between feeding trips. As that sea ice melts and breaks up earlier due to warming, their whole life cycle is disrupted. It puts their survival directly at risk.
Okay, penguins and sea ice. What about somewhere else?
Closer to home, maybe the Mount Rainier white-tailed ptarmigan. It's a bird that lives high up in the mountains, really adapted to snowy conditions.
Yeah.
As the climate warms, the snow patterns are changing, the areas they rely on are shrinking. They're literally losing their specialized habitat. Fewer places to live, fewer places to breed.
And didn't you mention something about the Salton Sea in California? That sounds like a combination of issues.
Exactly. The Salton Sea is a really stark example. It's suffering from climate change. Higher temperatures mean more evaporation, making the water much, much saltier. But it's also hit by agricultural runoff, pollution.
Yeah.
The result, massive fish die-offs. And that devastates the huge numbers of birds, including endangered species, that rely on those fish for food. Plus, as the sea shrinks, it exposes this dry lake bed.
Which causes dust storms?
Yeah, huge dust storms, impacting air quality for miles around. It's a real environmental mess, driven by climate change and other human pressures combined.
It really shows how interconnected everything is. Okay, let's shift focus a bit. How do these big global issues play out in specific places? Brazil, for instance, it's famous for biodiversity. How are things there?
Brazil is, an absolute giant of biodiversity. You've got the Amazon rainforest, the Atlantic forest, incredible ecosystems. But the threats are immense, too.
Deforestation, I assume.
Huge amounts of deforestation, yes. But also, wildlife trafficking is a massive problem in Brazil. Illegal trade in animals.
Really? What kinds of animals?
Get this, it's estimated that something like 80% of the animals trafficked there are birds.
80%? Just birds? Why birds?
Well, think about it. Beautiful plumage for decorations, unique songs for the pet trade. Sometimes just the rarity itself makes them valuable to collectors.
Wow.
And here's a really worrying thing. The rarer a species becomes, often the more valuable it gets on the black market.
So it creates like a feedback loop. The more endangered it gets, the more people want to illegally capture it.
Precisely. It's a terrible cycle. Scarcity drives up the price, which increases the incentive for poaching, pushing the species closer to extinction. Really perverse.
That's deeply worrying. And I think I read that there have been concerns about environmental policy changes in Brazil recently?
Yes, conservation groups and experts have definitely raised alarms. There have been reports about environmental agencies being weakened or having their funding cut, regulations being rolled back. There was even a high-profile case where an agent who fined a powerful figure for illegal fishing was reportedly demoted and fines were revoked. Things like that send a really bad signal about enforcement.
Yeah, that doesn't sound good for protecting wildlife. But is it all bad news from Brazil? Are there any bright spots?
Oh, absolutely. There's a fantastic success story. The golden lion tamarin.
Ah, the little monkey.
That's the one. A beautiful little primate. It was critically endangered, really on the brink. But through a massive coordinated effort, Awareness campaigns, government action, NGOs.
What kind of awareness campaigns?
They even put the tamarin on Brazilian banknotes. That really raised its profile. And the result, the population recovered significantly. It was a brilliant example showing that dedicated conservation can work.
That's fantastic. A bit of hope there. Okay, let's swing over to the United States. What's the situation with endangered species there?
Well, in the U.S., there's a pretty clear link shown in data between where lots of people live and where you find more threatened and endangered species. More human population density often means more pressure on wildlife.
Makes sense. And the main law is the Endangered Species Act, right, from the 70s?
That's right, the Endangered Species Act, or ESA, from 1973. It's the cornerstone. It allows species to be formally listed as either endangered or threatened.
What's different?
Endangered is more critical, facing extinction now. Threatened means likely to become endangered in the foreseeable future. An example of an endangered one under the Act is the Salt Creek tiger beetle, a very rare insect found only in a small area of Nebraska.
Okay. And who decides what gets listed?
Primarily two federal agencies. The U.S. Fish and Wildlife Service for terrestrial and freshwater species, and the National Marine Fisheries Service for marine species. They handle the classification, develop recovery plans, and enforce the protections.
Is that process straightforward or controversial?
Oh, it can definitely be controversial. There are often debates about, the scientific evidence used for listing or delisting when a species recovers. And a big one is land use restrictions.
Because protecting habitat might mean people can't develop their land.
Exactly. That causes conflict. There's lobbying from industries, political pressure, plus how much weight is given to the advice of wildlife experts can kind of shift depending on who's in charge politically at the time. It's a real balancing act.
Yeah, I can imagine. Are there any, downsides to actually listing a species? Unintended consequences?
It's complex. Sometimes, sadly, yes. Making a species officially endangered can, perversely, make it more attractive to illegal collectors or poachers because of its rarity.
Oh, no. Like the Brazil situation?
A bit like that, yeah. On the flip side, sometimes legal commercial farming can potentially help.
Yeah.
Like with turtle farming in China, the idea is if you can farm them legally, maybe it takes pressure off the wild ones. But, as we'll touch on, that's not always straightforward either.
Right.
And then there's this really unfortunate thing called the shoot, shovel, and shut up problem.
That sounds ominous. What is it?
It's where some landowners might secretly kill endangered animals they find on their property because they're afraid having the animal there will restrict how they can use their land or lower its value. So they try to hide the evidence.
That's awful. But despite these issues, how effective is the ESA overall? Is it working?
Generally, yes. While business groups sometimes criticize it, most wildlife scientists see the ESA as really important and largely successful. 19 species have recovered enough to be taken off the list entirely.
Okay, that's positive.
And in the Northeast U.S., for example, studies show that for 93% of the listed species, their populations are either stable or actually increasing. So it's definitely making a difference in preventing extinctions.
Good to know. How many species are currently listed in the U.S. ballpark?
Right now, it's around 1,556 species listed as endangered or threatened under U.S. law.
Okay.
But, and this is important, that number doesn't capture all the species actually in trouble. Organizations like NatureServe, which do independent assessments, estimate that a much higher percentage of U.S. vertebrates, plants, and even fungi are imperiled, maybe somewhere between 7 and 18% of known species.
So the official list is just the tip of the iceberg, really?
In many ways, yes. There are likely many more species facing serious risks than are currently getting formal protection out of the Act. It makes you think about the past, too.
How so? Have we caused extinctions before on this scale?
Oh, absolutely.
Yeah.
Overhunting and overfishing have historically been huge drivers of extinction and near extinction. Think of the dodo or the passenger pigeon. There were billions of them, and they were hunted to extinction.
Billions. Wow.
Yeah. And the American bison, the buffalo, nearly went extinct. Same with the bald eagle, our national symbol. It was almost wiped out.
But the bald eagle came back, right?
It did. That's
Yeah.
a major conservation success story. Habitat protection, legal protection, and crucially, banning the pesticide DDT, which was devastating their reproduction. Now they're back to least concern. It shows what's possible.
That's really encouraging. Are there modern examples of overexploitation causing problems?
Definitely. Look at whales. Even with international whaling bans and treaties like CITES regulating trade, several large whale species, blue, fin, humpback, sperm whales, are still listed as endangered.
Why is that? I thought whaling was mostly banned.
Largely, yes, but not entirely. Japan, for example, continues whaling, claiming it's for scientific research, which many conservation groups dispute. So the pressure hasn't completely gone away for these already vulnerable populations.
It seems like a constant battle. Okay, let's hop over to Canada. What's their approach? Similar to the U.S.
Somewhat similar, yes. Canada has the Species at Risk Act, or SARA. It designates species as threatened or endangered if they're facing imminent extinction or extirpation.
Extirpation, what's that?
That means they're extinct just within Canada, even if they still exist elsewhere. Like if grizzly bears disappeared from Canada but still existed in the U.S.
Ah, okay. Local extinction.
Right. And under SARA, once a species is listed, they're required to develop recovery plans to try and bring the population back. As of 2021, Canada had officially assessed 369 species as endangered.
Okay. And one more region, India, another biodiversity hotspot. What are the key concerns there?
India faces huge challenges too. The Worldwide Fund India has flagged serious concerns for iconic species like the red panda, the Bengal tiger, the Ganges river dolphin, which is really unique, and the Asian elephant.
What are the main threats there? Similar things.
Yes, habitat loss is a major issue with India's large human population, and poaching remains a persistent threat for tigers, elephants, and others. To fight this, India has its own Wildlife Protection Act and is also part of CITES, that international trade convention.
Right. So we're seeing common themes everywhere. Habitat loss, illegal trade, climate change impacts. Feels pretty daunting. Let's focus now on the solutions. What's actually being done? What conservation efforts are out there?
There's quite a toolbox, actually. One well-known method is captive breeding.
Like in zoos.
Exactly. Breeding endangered species in zoos, aquariums, or special conservation centers. The idea is to build up a healthy, genetically diverse population in a safe environment, with the ultimate goal of potentially reintroducing them back into the wild.
Does it work?
It can. There have been successes. But it can be tricky, especially for animals that migrate long distances or have really complex social lives. And you always have to be careful about inbreeding if your captive group is too small.
I know zoos coordinate on this stuff, right? There's some kind of plan.
Yes, the Association of Zoos and Aquariums, AZA, runs the Species Survival Plan, or SSP. It's a big collaborative effort.
How does it work?
Over 450 different SSP programs exist, each focused on a specific endangered or threatened species. They manage the populations across all participating AZA institutions, making recommendations on who should breed with whom to maintain genetic diversity. Think giant pandas, gorillas, California condors, they're all part of SSPs. It's like a genetic safety net.
That sounds really important. What about other approaches? I think you mentioned private farming earlier. How does that work for conservation?
Yeah, it seems counterintuitive sometimes, but private farming can be a powerful tool. The best example is probably rhinos in southern Africa.
Farming rhinos.
Well, ranching them, essentially. Private landowners found that if they could manage rhinos on their land and benefit economically, maybe through tourism or sometimes through regulated sales of live animals or controlled hunting, it gave them a strong incentive to protect the rhinos from poachers. And it worked. Populations of both black and white rhinos increased significantly on private lands there.
So aligning economic benefits with conservation.
Exactly. When local people or landowners see a direct value in keeping the animals alive, it can be very effective. But it's not always simple. Remember the turtle farming in China?
Right. You said there were concerns.
Yeah. While farming millions of turtles likely reduced the number taken directly from the wild for food, there's still this issue. Some farms apparently prefer to catch wild turtles to use as breeding stock. They think they're somehow better or more genetically robust.
So even with the farms, they might still be taking endangered turtles from the wild.
That's the concern, yes. So while farming can help, it needs careful management to ensure it doesn't inadvertently harm the very populations it's supposed to protect. It's nuanced.
Okay. Any other innovative ideas? Like for overfishing?
There's some really interesting work happening with aquaculture. For instance, in Australia, researchers managed to breed southern bluefin tuna, a heavily overfished species, completely in landlocked tanks.
Wow, tuna in tanks.
Yeah, from egg to adult, totally separate from the wild ocean populations. If that kind of technology can be scaled up, it offers hope for taking massive pressure off wild fish stocks.
That's potentially huge. Okay, amidst all the challenges, let's end on some high notes. Can you share some clear-cut success stories where conservation really turned things around?
Absolutely. There's some really inspiring ones. The Hawaiian monk seal, for example. They were in steep decline.
What did they do?
A combination of things. reducing conflicts with fisheries, rehabilitating sick or injured seals, protecting critical habitat, intense monitoring. It took a lot of effort, but their numbers have started a slow, gradual climb back up.
That's great news.
And we already mentioned the American bald eagle, a massive success. From near extinction due to DDT and habitat loss to being delisted entirely. Shows what happens when you identify the core problem in that case, the pesticide, and take decisive action.
Classic example. Any others?
The gray wolf recovery in Yellowstone is another big one. Wolves were gone from the park for decades.
Right, they reintroduced them.
Yes, in the mid-90s, and it had amazing ripple effects through the whole ecosystem. Beavers came back, vegetation changed, it was incredible. And wolf populations have recovered so well in the northern Rockies that they've been delisted in several states, though that remains controversial sometimes.
Fascinating. One more.
Okay, how about the Channel Island fox? These are tiny foxes living on islands off California. Several subspecies were crashing towards extinction due to non-native predators like golden eagles and habitat changes caused by feral pigs.
What saved them?
A really intensive, multi-pronged effort. Captive breeding, removing the non-native golden eagles, actually reestablishing native bald eagles, which deter the golden eagles, getting rid of the feral pigs. It was complex.
And it worked.
Amazingly well. So some subspecies, it's considered the fastest recovery ever for a mammal on the endangered species list. They bounced back remarkably quickly once the threats were managed.
Oh, wow, those are fantastic stories. They really show it can be done, right? Focused effort can make a massive difference.
Definitely. It takes science, dedication, resources, and often difficult choices. But saving species from the brink is achievable.
Okay, so wrapping up this deep dive.
Yeah.
What are the main takeaways you want people to remember?
Well, first, understanding what endangered means and the scale the IUCN Red List helps there.
Yeah.
Second, recognizing the primary drivers, mostly us, through habitat loss, poaching, invasive species, and increasingly climate change. Third, seeing how this plays out differently across the globe, in places like Brazil or the US or India, each with unique challenges. And finally, knowing that there are solutions. Captive breeding, smart farming, habitat restoration, legal protections, and we have real success stories that prove conservation works.
That's a great summary. And one final thought to leave us all chewing on, something provocative.
Maybe just this. Think about that web of life. Every species is a thread. When a thread breaks, when a species disappears, it weakens the whole tapestry. It affects ecosystems in ways we might not even foresee. So the fate of endangered species isn't just about saving cute animals, it's fundamentally about the health and resilience of our entire planet, the planet we depend on too. It forces us to ask, what's our responsibility here? What value do we place on biodiversity? And what are we truly willing to do to protect it for the future?
A really important question for all of us. If this conversation sparked your interest, please do explore further. Check out the IUCN Red List website or look up conservation organizations working on species you care about. There's so much more to learn. Thanks for joining us on this deep dive.
Welcome to the Deep Dive. Today, we're plunging into the fascinating world of hormones.
Ah, yes, those tiny but incredibly mighty messengers.
Exactly. They orchestrate so much of what happens in our bodies, and, even in plants and fungi, too.
It's quite amazing the reach they have.
We've gathered a whole load of information, mostly drawn from the Wikipedia article on hormone.
Right.
And our mission, really, is to pull out the most interesting bits, those aha moments, without getting too bogged down in technical terms.
Sounds like a good plan. Keep it accessible but thorough.
So the word hormone itself, it comes from a Greek word meaning setting in motion. Isn't that just a perfect description?
It really is. It immediately gets to their core function as signaling molecules.
Right.
Think of them like the body's internal postal service, maybe, sending messages far and wide.
Yeah, from one group of cells to another, sometimes over huge distances, relatively speaking.
Exactly. And these messages, they're all about regulating physiology and behavior. It's hard to think of a major biological process they don't touch.
Absolutely. And what's really striking, I think, is the sheer variety of molecules we call hormones.
Oh, definitely.
It's not just the famous ones like, say, insulin or estrogen. The definition actually includes things like eicosanoids.
It's like prostaglandins, yeah.
Steroids, of course, like estrogen. Amino acid derivatives like adrenaline. Proteins, peptides like insulin, and even gases ethylene, for example.
It's a remarkably diverse chemical toolkit for communication.
Why is there such a mix, do you think? Such different structures doing this job?
Well, that diversity is actually key. It allows for this incredible range of actions hormones can have. Different chemical properties mean they interact with different receptors
Oh, okay.
and trigger very distinct responses inside the cell. Whether they're water soluble or lipid soluble makes a huge difference in how they travel and act.
Right, how they get around and talk to the cells.
It's a beautiful example, really, of evolution using chemistry to solve all sorts of biological problems.
That makes sense. So, thinking about how they communicate, it's all about coordinating things between organs and tissues, isn't it?
Precisely. In us vertebrates, hormones are basically running the show for digestion, metabolism, breathing, sleep, senses, mood, reproduction. The list goes on.
And it's not just animals. Plants rely just as heavily on them, guiding almost their entire life cycle.
From germination right through to, well, the end. Senescence.
So how does that work, fundamentally, the message getting through?
The core mechanism is the hormone traveling to its target cell and binding to a specific receptor protein there.
Like a key fitting into a lock.
Exactly like that. And that binding event, that's what kicks off a chain reaction inside the cell, a signal transduction pathway.
Yeah.
Often this ends up changing gene expression, basically telling the cell's DNA to make more or less of certain proteins.
So the hormone delivers instructions right to the genetic level, potentially.
In many cases, yes, though there are other non-genomic pathways too.
Okay, so the hormone docks with its receptor, and then stuff happens inside. You mentioned water-soluble versus lipid-soluble affecting this.
Right. It really comes down to that. Water-soluble ones, like peptides, generally can't just slip through the cell's fatty membrane.
Makes sense. Oil and water.
Pretty much. So they bind to receptors on the cell surface. This then triggers the production of second messengers inside the cell.
Ah, okay, like passing the message on.
Exactly, passing the baton down the line. Lipid-soluble hormones, like steroids, however, can cross that membrane easily.
Because they're fatty themselves.
Right. So they often go straight into the cell, sometimes into the nucleus itself, and bind to receptors there that directly influence the genes, delivering the message straight to the command center, so to speak.
That's a neat distinction. Direct delivery versus relaying the message.
Although, interestingly, you have things like brassinosteroids in plants. They're lipid-soluble steroids, but they mostly bind to surface receptors.
Huh. So biology always has exceptions, doesn't it?
It certainly keeps things interesting. It shows these aren't always rigid categories.
So how do these hormones get where they need to go? They can't just float around randomly, surely.
No, definitely not. In vertebrates, we have specialized endocrine glands, the thyroid, adrenal glands, ovaries, testes, pituitary, and so on.
The hormone factories.
Essentially, yes. They produce and secrete hormones directly into the bloodstream.
And what triggers that release?
Usually it's a specific biochemical signal, and very often it's regulated by negative feedback loops.
Okay. Explain negative feedback quickly.
It's a self-regulating system. Imagine your blood sugar goes up after a meal. Your pancreas releases insulin. Insulin helps cells take up sugar, so blood sugar drops. That drop in blood sugar then signals the pancreas to release less insulin.
So the effect of the hormone switches off its own production, like a thermostat.
Exactly like a thermostat or cruise control in a car. It maintains balance or homeostasis.
Got it. So the glands dispatch the hormones into the blood. How do they travel then? Especially those lipid-soluble ones that don't like water.
Good question. Water-soluble ones generally dissolve fine and travel freely, but lipid-soluble hormones need help. They usually bind to carrier proteins in the blood plasma.
Like little ferry boats for the hormones.
That's a great analogy, like thyroxine-binding globulin carrying thyroid hormone. This protects them, helps them travel, and actually extends how long they last in the body.
And are hormones always released ready to go?
Not always. Some, like insulin, are released in their active form. Others are secreted as inactive precursors called prohormones.
Prohormones.
Yeah, they need to be activated later, often in the target tissue itself or somewhere else in the body. It's another layer of control.
And just to clarify, endocrine glands secrete into the blood, right? What about exocrine?
Right. Endocrine is ductless, straight into the blood via leaky capillaries called fenestrated capillaries. Exocrine glands use ducts, think sweat glands or salivary glands. And then there's paracrine signaling too.
Yes, you mentioned that earlier. What's that again?
Paracrine hormones just diffuse locally to act on nearby cells without entering the main bloodstream, like neighborhood gossip instead of a national broadcast.
Okay, nice analogy. So vertebrates have this fairly centralized system with glands. But plants don't have glands, you said. How do they manage?
That's a key difference. Plant hormone production is much more distributed, more decentralized.
So no central factories.
No. For instance, auxin, which controls growth, is mainly made in the growing tips of shoots and young leaves. And where hormone is made in a plant can change with its age or the environment. It's more flexible, perhaps.
Interesting. So if we trace the whole journey of a hormone molecule,
Okay, let's map it out.
it's made somewhere,
Biosynthesis, yeah.
stored maybe, then released,
Secretion.
travels to the target cell,
Transport.
gets recognized by a receptor,
Recognition. Crucial step.
triggers a response inside.
Signal relay and amplification, the transduction part, leading to the cellular response.
And that response might feed back to control the start of the process.
Exactly, the feedback loop for regulation.
And eventually the hormone gets broken down.
Degradation, yep. Got to clear the signal. It's quite an intricate sequence.
It really is. And understanding each step is key. Now, how do we even figure all this out? The history must be fascinating.
Oh, it is. The discovery of hormones is a great story of scientific detective work.
Where did the first hints appear?
One of the real landmark moments was way back in 1849 with Arnold Adolf Berthold.
Berthold, okay. What did he do?
He was studying roosters, specifically what makes male the comb, the waddle, the crowing, the behavior.
Right.
He knew that castrating them, removing the testes, stopped them developing these traits. Standard practice even then.
Okay.
But then he did something clever. He took the testes out of some young roosters. As expected, they didn't develop normally. But then he took one of those remove tests and put it back into the rooster's abdomen, just loose in there.
Really? Just dropped it back in?
Yep. And amazingly, those roosters developed pretty much normally. Their combs grew, they crowed, they acted like typical roosters.
Wow. So it didn't matter that the testes weren't connected by nerves or anything?
Exactly. He even transplanted tests between different roosters, and it still worked. The key insight was brilliant.
It must be releasing something into the blood.
Precisely. Berthold concluded the testes secrete some chemical substance carried by the blood that's essential for maleness. He didn't know it was testosterone, of course, but he demonstrated the principle of endocrine signaling. Foundational stuff.
That's incredible. Just from observing roosters, what came next?
Well, fast forward a few decades to the 1880s. Charles Darwin and his son Francis.
The evolution guy, what were they looking at?
They were studying plants, specifically how they bend towards light phototropism.
Oh, okay.
They noticed the very tip of a young shoot seemed to sense the light, but the bending actually happened lower down the stem.
So the sensor and the responder were in different places.
Yes. They proposed that some kind of transmissible substance must be sent from the tip down to the bending region to signal it.
A transmissible substance. I like that, like Berthold's chemical.
Very similar idea, yeah. Chemical communication within the organism. It wasn't immediately accepted. Some doubts remain.
Science being science.
But it spurred more research. Later, in the 1920s and 30s, scientists like Fritz Wendt and Nikolai Chalodny showed pretty definitively that an uneven distribution of a growth-promoting chemical caused the bending.
They pinned it down.
They did. And that substance was finally isolated in 1933 and named auxin, the first plant hormone identified.
So from roosters to plant shoots, the idea of chemical messengers was gaining ground. What about the first named hormone in animals?
That usually goes to George Oliver and Edward Schaefer in 1894. They were working with extracts from the adrenal glands.
Adrenals, okay. Above the kidneys.
Right. They found these extracts contained something incredibly potent, we now know it as adrenaline, or epinephrine, that caused dramatic physiological changes, like increased heart rate and blood pressure.
The fight or flight response stuff.
Exactly. Interestingly, people sometimes mistakenly think secretin was the first hormone discovered, but adrenaline actually predates it slightly in terms of identification of its effects from an extract.
Okay, so adrenaline was identified early on, but then secretin was important, right?
Hugely important. This was in 1902 with William Bayliss and Ernest Starling. They were investigating digestion, specifically how the pancreas knows when to release its digestive juices into the intestine.
What was the thinking then? Nerves.
Mostly, yes. The assumption was it was all controlled by nerve signals from the intestine to the pancreas.
But Bayliss and Starling suspected otherwise.
They did. In a really elegant experiment, they cut all the nerves going to a dog's pancreas. But when they introduced acidic food content from the stomach into the intestine, the pancreas still secreted its juices.
So it couldn't be the nerves.
Exactly. They figured there had to be a chemical messenger released by the intestinal lining into the bloodstream that traveled to the pancreas and stimulated it.
And they found it.
They did. They extracted it, named it secretin, and crucially, it was Starling, a bit later, who proposed the general term hormone for these types of blood-borne chemical messengers.
So he coined the word.
He did. And their work really established that the nervous system wasn't the only major control system in the body. There was this whole other chemical signaling network.
These historical experiments are just fantastic. Really clever work. Okay, let's jump back to the different ways hormones communicate. We covered endocrine long distance via blood. What were the others again?
Right. Besides endocrine, we have paracrine signaling.
The neighborhood gossip one.
Yeah. Acts on nearby cells, no need for the general circulation. Very local effect.
Okay.
Then there's autocrine signaling. That's where a cell releases a hormone that acts back on itself.
Talking to itself. Self-regulation.
Pretty much. A form of cellular feedback. And finally, intracrine signaling.
Intra, meaning within.
Exactly. The hormone is made and acts inside the same cell without ever being released.
Wow. So broadcast, local chat, self-talk, and internal monologue. Different scales for different needs.
That's a great way to put it. It allows for really precise control depending on the situation. Paracrine is vital in things like local inflammation or wound healing, for example.
Makes sense. Now, we said hormones are chemically diverse. Let's revisit those classes.
Okay. Remember, they're defined functionally, but we can group them chemically. In vertebrates, a big group is protein and peptide hormones.
Chains of amino acids, like insulin.
Exactly. Insulin, oxytocin, growth hormone. They're generally water-soluble, hydrophilic, and usually bind to receptors on the cell surface. Their blueprints are encoded directly in our DNA.
Okay, proteins, peptides. What else?
Amino acid derivatives. These are modified from single amino acids, often tyrosine. Think thyroid hormones or adrenaline and noradrenaline, the catecholamines.
Got it. Then the fatty ones.
Steroids, derived from cholesterol. They all share that characteristic four-ring structure.
Estrogen, testosterone, cortisol.
They're lipophilic, lipid-soluble, so they tend to cross cell membranes and bind to receptors inside the cell, often nuclear receptors that affect genes.
Okay. Any others?
Eicosanoids. These are derived from fatty acids like arachidonic acid. Prostaglandins and thromboxanes are examples. They often act locally on membrane receptors and are involved in inflammation, blood clotting, lots of things.
Right. Produced by enzymes like KOX1 and KOX2 that some painkillers target.
Precisely. And finally, believe it or not, simple gases can act as hormones.
Like ethylene in plants.
And nitric oxide, NO, in animals, involved in things like blood vessel dilation. So quite a range.
It really is. Does this classification hold for invertebrates and plants too?
Broadly, yes, but with variations. Insects, for instance, have unique hormones like juvenile hormone, which has a different structure. And plants have their own key players like auxins, cytokinins, gibberellins, abscisic acid, ethylene regulating their specific needs.
It shows how signaling systems evolve differently across life. Now, receptors, they're the gatekeepers, you said.
Absolutely critical. Highly specific proteins that recognize and bind just one type of hormone or maybe a few closely related ones.
The lock for the hormone key.
Exactly. And a single cell can actually have multiple different receptor types for the same hormone.
Really? Why?
It allows that one hormone signal to trigger different responses or pathways within the same cell, depending on which receptor it binds to. Adds complexity and flexibility.
Okay. And cells can have receptors for many different hormones too, right?
Oh, yes. Cells are constantly integrating signals from multiple hormones.
So where are these receptors found again? Surface versus inside?
Mostly depends on the hormone type. Peptides and most eicosanoids, being water-soluble, bind to surface receptors. Many of these are G-protein-coupled receptors or GPCRs.
GPCRs, okay. Common drug targets.
Very common. Binding there triggers those intracellular cascades, the second messengers.
And the lipid-soluble ones. Steroids, thyroid hormones.
They typically waltz right through the membrane and bind to intracellular receptors, often in the cytoplasm or nucleus. These are usually part of the nuclear receptor family.
And they directly affect genes.
Yes. The hormone receptor complex often acts as a transcription factor, turning genes on or off. Though, again, there are exceptions. Some steroid receptors have been found on the cell surface, too, allowing for faster, non-genomic effects.
Always nuances. Okay, zooming out again. What are the big picture effects of hormones in humans? It feels like everything.
It's pretty close to everything. They stimulate or inhibit growth. They regulate our sleep-wake cycles, our circadian rhythms.
Definitely feel those.
They profoundly influence mood. They can trigger or prevent apoptosis-programmed cell death. They activate or suppress the immune system.
Wow.
Huge role in metabolism, how we process energy. They prepare the body for, well, for action. Mating, fighting, fleeing.
The 4 Fs sometimes.
Okay? Something like that.
Huh.
They guide us through life stages, puberty, parenting, menopause, control reproductive cycles, influence hunger and cravings.
Oh, much control.
And they even regulate each other. Hormones control the release of other hormones. It's all geared towards maintaining that internal balance, homeostasis.
It's an incredibly intricate web.
Yeah.
How is it all kept in balance? It can't just be hormones firing off constantly.
No, precise regulation is key. And as we said, negative feedback is a major player. The effect of the hormone usually inhibits its own release.
The thermostat principle again, like insulin and blood sugar.
That's a classic example. But hormone secretion is also influenced by other things.
Such as?
Other hormones, for one. You have releasing hormones and inhibiting hormones that control endocrine glands. The concentration of ions or nutrients in the blood plasma matters, like calcium levels affecting parathyroid hormone.
Right.
Even nerve signals and mental activity play a role. Think about stress triggering cortisol release and environmental cues like light affecting melatonin for sleep.
It's all connected. What about tropic hormones? I hear that term.
Tropic hormones are hormones whose main job is to stimulate another endocrine gland to produce its hormones.
Like a middle manager in the hormone hierarchy.
Kind of, yeah. Thyroid-stimulating hormone, TSH, from the pituitary, tells the thyroid gland to make thyroid hormones. It's a common control mechanism.
And you mentioned prohormones earlier, storing inactive forms.
Right, that allows for rapid release of active hormone when needed. And those eicosanoids, the local ones, they're usually broken down really quickly, keeping their action contained.
Regulation happens at the receptor level too, right? Agonists and antagonists?
Yes. Agonists are molecules that bind to a receptor and activate it, mimicking the hormone. Antagonists bind but don't activate, they just block the real hormone from binding. Many drugs work this way.
So many layers of control. Given their power, it's no surprise we use hormones as medicine.
Absolutely. Hormone therapy is a huge field. Think estrogens and progestogens in birth control pills or hormone replacement therapy, HRT.
Thyroxine for underactive thyroid.
Steroids like cortisol analogs for inflammation or autoimmune diseases, insulin for diabetes, obviously, even adrenaline and local anesthetics sometimes, steroid creams for skin conditions. The list is long.
And when used therapeutically, the doses might be different from natural levels.
Often, yes. A pharmacologic dose, or supraphysiological dose, means giving much more hormone than the body normally makes.
I do that.
It can produce different, sometimes stronger effects. High-dose glucocorticoids, for instance, are powerful anti-inflammatories, way beyond their normal metabolic role. But higher doses often come with more side effects, especially long-term.
Right, trade-offs. Now, let's talk behavior. Hormones clearly affect physiology, but the link to behavior seems complicated.
It is complex and definitely bidirectional. We can learn a lot by measuring hormone levels, looking at release patterns, mapping receptors in the brain.
But it's not like hormone X directly causes behavior Y.
Rarely that simple, no. It's more about probability. Hormones tend to influence the likelihood or intensity of a behavior by tuning neural circuits or physiological states that underpin it. They're modulators, not simple triggers.
So they might make you more likely to feel aggressive, say, but don't force you to act on it.
Exactly. It's one influence among many. Experience, social context, genetics all play roles. And crucially, behavior feeds back onto hormones.
How so?
Well, winning a competition might raise testosterone, which might then influence future competitive drive. Stressful situations trigger cortisol release. Our actions and environment constantly shape our hormonal landscape. It's a dynamic loop.
And scientists have ways to try and pin down these links.
They look for correlations. Does the behavior frequency match hormone levels? Does removing the hormone source reduce the behavior? Does adding the hormone back restore it? It requires careful study.
Okay. Now, a common point of confusion. Hormones versus neurotransmitters. How are they different?
They're both chemical messengers, but they operate differently. Key differences are scale and speed.
Scale.
Hormones act over larger distances, potentially body-wide via the bloodstream. Neurotransmitters act very locally, across a tiny gap, the synapse, between two neurons, millimeters versus micrometers. Hormones are slower seconds, minutes, hours for effects. Neurotransmitters are super fast milliseconds. Think nerve impulse speed versus blood flow speed.
Okay. How they travel is different too, blood versus nerve tracks.
Right. And the signaling itself. Neural signals are often seen as digital all-or-nothing action potentials. Hormonal signaling is more analog, graded by concentration.
Clear differences then. Broader, slower blood-borne signals versus fast, targeted nerve signals. What about neurohormones? They sound like a mix.
They are. They bridge the gap. Neurohormones are produced by special nerve cells, neuroendocrine cells, that receive nerve input but release their chemical messenger into the bloodstream, like a hormone.
So the nervous system sends an electrical signal, which causes a chemical release into the blood.
Exactly. The hypothalamus controlling the pituitary gland is a classic example of this neuroendocrine link. The brain uses the hormonal system for long-range communication.
Fascinating integration. Okay, one last thing to circle back on. Those hormone-binding proteins.
Yeah.
More than just transport ferries.
Definitely. By binding hormones, they increase their half-life, letting them stick around longer. They also act as a buffer, a reservoir.
How did that help?
It smooths out fluctuations in the level of free hormone, the active form. If free hormone levels drop, some can unbind from the protein to replenish the pool, maintaining a more stable signal. Thyroxine-binding globulin does this for thyroid hormone, essential function.
Got it. Okay, let's try and wrap this up. We've covered a lot of ground on hormones.
We certainly have.
From their basic definition as diverse signaling molecules setting things in motion,
Derived from that Greek word, yeah.
to how they communicate via receptors, the different chemical types, the intricate ways they're secreted, transported, and regulated through feedback loops.
We looked at the history, too, Berthold's roosters, the Darwin's plants, secretin, adrenaline, key moments.
And the different signaling types, endocrine, paracrine, autocrine. Plus, their huge range of effects on growth, mood, metabolism, reproduction, essentially touching everything.
Don't forget their use in medicine, the complex link with behavior, and how they differ from, but also connect with, neurotransmitters via neurohormones.
Right. It's clear these tiny molecules have an immense fundamental role in life.
Absolutely. Understanding them is key to understanding biology, medicine, and even ourselves. They really are the hidden orchestrators.
So here's a final thought to leave you with. Given how profoundly these small molecules influence us, and how sensitive their regulation is, how might subtle things in our environment, or maybe even our own thoughts and stress levels, be creating ripple effects through our hormonal systems in ways we're only just starting to understand?
That's a deep question. It really highlights the intricate connections between mind, body, and environment.
Definitely something to ponder. Thanks for joining us on this deep dive.
My pleasure.
Until our next exploration.